Head-CED BIS. Now I would like to request Dr. V Ramachandra to come on the dais and chair this session. I would also request Shri and Bhadra to please come on the dais and co-chair this session. To represent NCB, I would like to call Dr. Sanjay Mundra, General Manager NCB, to please come on the dais and take this session forward. Thank you. Again, it is requested to all the presenters to be seated till the end of this session. Certificates would be given to all the presenters. Thank you, sir.
Hello. So I welcome, this is our evening session, our chairman Dr. V Ramachandra ji and our co-chairman Shri ji Bhadra. So this session is for the, second C is the latest innovation trends. So I request our chairman Dr. V Ramachandra to start with the session. Thank you.
Thank you, sir. A very good evening to all of you, ladies and gentlemen. Being aware that this is the last session, we'll straight away move on to the first. The next presentation is from the group from Indian Institute of Science, Bangalore, Sahana and Souradeep Gupta, who will present. Yeah, Sahana is there. This is on the development of activated biochar and its application in concrete. Yeah. That is the one. Yeah. Sahana, you have a total of 8 minutes. Yeah. Please conclude. Maybe initial introduction and things like that you can skip and then directly go to it.
Thank you. Okay, very good evening all. My name is Sahana CM. Today I'll be presenting on developing activated biochar and utilizing in the concrete. These are the outlines for my presentation. The building carbon footprint is over its lifespan is the combined sum of the embedded and operational emission. The share of embedded carbon emission is about to increase 25 to 51% by 2050. Meanwhile, the operational carbon emission is about to shrink, like due to electricity goods increasingly transition to renewable sources. And looking into biomass waste management, the first one is the open burning. Open burning is leading to environmental issues and so many issues. But is it the solution is the incineration? Then what about the emission and all? Like incineration of 1 kg of mixed waste is releasing about 0.7 to 1.2 kg of CO2. That is very similar to the production of OPC. And also 33 to 50% of emission is from the biogenic carbon. Then how about using raw biomass in the application of the cement? But the major challenges are like degradation of hemicellulose and sugars in alkaline solution, and also retardation of cement hydration, and longer setting time, and also risk to durability of concrete. One of the possible solutions of waste management is the pyrolysis method. The feedstock for the pyrolysis is the biomass, which is like includes agricultural waste, food waste, and wood waste. The key products from the pyrolysis are synthetic oil, gas, and biochar. The biochar has a wide range of application, like soil enhancing properties. In our case, it is a additive or a cement replacement. The biochar is a solid material obtained from thermal decomposition of organic material under very limited supply of oxygen and relatively at lower temperature. And the appearance of the biochar is very similar to the coal, but the production of biochar is mainly depends on pyrolysis condition and feedstock. Looking into biochar as a carbon sequestration material, in perspective of environmental benefits, the pores of the biochar absorbs carbon dioxide and sequester as in the pores, and also reduces the waste and cuts the greenhouse gas by about 870 kg of CO2 per ton dry feedstock. And also it could be able to reduce about 12% of global emission annually. And how does it works in the concrete? The finer biochar particle acts as a filler in the air voids, and also the pores of the biochar provide additional surface for water storage and nucleation for cement hydration. And it will increase the local motor density and avoid excess water that leads to air voids upon evaporation. And also one of the potential solution for the rising emission is the sequestering carbon in the cementitious material. And biochar is the great replacement in the cement for that solution problem. Objectives of the presentation is to enhance the physical characteristics of the biochar through chemical activation and to improve the hydration kinetics by addition of whatever the modified biochar and evolution of engineering performance. Looking into material synthesis, biochar is carbonized using chemical activator at different activation temperature and impregnation ratio. The purpose of activation is to increase the micropore volume, which is ideal for carbon adsorption. And looking into XRD results, main traces are like calcite and quartz found. How does this activation mechanism works? These alkali metal ions have the ability to power any material, binding ability. And in aqueous solution, the potassium ions randomly distribute and free to move. So this energized potassium ions will penetrate into biochar to create the porous structure. And the final stage washing process has been done by both acid and water to remove the impurities and excess potassium adsorbed in the pores. And also from the observation from the activation, it is found that the surface area is almost increased by 300%, like activating at 750 degrees centigrade, and with the impregnation ratio of 1:3. And it has a direct relation with the pore volume. So as the activating the whatever the micropore volume existing will widen into mesopore, and formation of new pores and ultra micropores has been happened. And looking into the biochar and modified biochar added into the cement mortar, whatever the first graph you are looking, that is the only 100% OPC cement paste, and all other are 2% replaced with the biochar, both activated and non-activated. It is found that in biochar added mixes, biochar will absorb the water in the pores and slowly releases. It will leads to continuous hydration. And biochar activated at higher temperature increase the hydration, continuous hydration due to its higher porosity and surface area. And looking into microstructural images, it is we can see that the bonding of the biochar with the cementitious matrix has been increased, and it will be lowering the permeability of the concrete. And looking into ordnance state properties, replacing 2% of the cement replacement, there is little improvement in the strength, and a similar observation made in water accessible porosity. And looking into the micropore volume, whatever the biochar activated at high temperature, the micropore volume is reduced by 15% with respect to the cement paste. And summary is the KOH activation results in a higher specific surface area by almost 300%, and total pore volume almost increased by 220%. And also biochar activated at the high temperature enhanced the hydration kinetics, and addition of 2% biochar with the weight of the cement, even there is no much significant improvement in the strength, but there is a expecting great results in the carbon emission, and also like reduced environmental impacts, improved material properties, and also opportunity to contribute to the circular economy. Thank you.
Thank you. If there are any questions, we will take it later. Thank you very much for the presentation. The next presentation is by Dr. S.K. Singh's team, who will present. Jyoti will present. Jyoti, Himanshu, Chouhan. Influence of solid and liquid activators on the performance of slag-based composite binder.
Okay. A very good evening to everyone. So, myself Jyoti, research scholar at ACSR, CSR, CBRI, Roorkee. So today I am going to present my topic, that is influence of solid and liquid activators on the performance of LD slag-based composite binder. Okay. So here are the content of my presentation, which includes introduction, objective and experimental design, experimental work, results and discussions, conclusions, and publication for reference. So here is the introduction. As we know that steel industries produce various solid waste materials such as blast furnace slag, steel slag, specifically steel slag, and in which quantum of steel slag such as Linz-Donawitz LDS increases exponentially yearly. Now LDS is a crystalline material with similar mineralogical phases to OPC. Hence its utilization as binder is a promising due to both resource conservation as well as waste utilization. Due to the crystallinity of LDS, it has low reactivity, which needs to be addressed with the help of chemical activators. Now it is therefore important to identify the type of activators such as solid or liquid for maximum efficiency. So here is the objective and experimental design. So our objective is to develop newer cementitious binder using Linz-Donawitz slag and evaluation of the effect of activator type on the composite binder. So this is the experimental design, which includes a thorough characterization of LD slag, then mechanical processing of LD slag and optimizing the particle size, then the binder formulation and the paste fabrication. And 3 different batches were produced with the control and then ground LDS with the OPC and solid activator, in which 30% replacement of OPC has been done, and then ground LDS plus OPC plus liquid activator, in which also 30% replacement of OPC has been carried out, and then the sustainable composite cement has been optimized. So these are the materials which are used for the study. The first one, that is OPC 43 grade sourced from Ultratech Cement India. The Linz-Donawitz slag, which is procured from Tata Steel Jamshedpur India, and the laboratory reagent grade sodium hydroxide and sodium silicate procured from Thomas Baker India. So this is the chemical composition of LDS, which shows that it majorly contains calcium oxide, silica, iron content, and magnesium oxide. And other oxides are in relatively lower quantity. So here is the characterization of the material, which shows that it is a basic slag with a pH value of 11.72 and specific gravity of 2.55, and the particle size of the as received LD slag is 41.33 micron for the 90% of particles are below the 41.33 microns. And as per the XRD results, it has been observed that it has similar phases to OPC, such as dicalcium silicate, tricalcium silicate, calcium carbonate, dicalcium ferrite, and calcium hydroxide. And from the FESM images, it was observed that it has irregular surface texture and angular shaped particles. So this is the characterization. And here is the consistency and setting time of the different mixes produced with the different proportions of LD slag, which shows that the consistency of the OPC LDS mixes increased with increasing LDS, and also beyond 30% setting time was significantly reduced. So here is the mix composition, and 6 different mixes were produced with 30% addition, 30% substitution of LDS, and 2 different activators, that is NaOH and sodium silicate, were used both in solid as well as in liquid form, and the water binder ratio was kept constant, that is 0.45, and here is the specimen preparation. So after the specimen preparation, the strength analysis was carried out, and it was observed that mixes with solid sodium silicate, that is mix 3 and mix 4, they have higher strength than mix 1 and mix 2, that is the solid sodium hydroxide based mixes, and the mix 6, which is based on the liquid sodium silicate, exhibit higher strength values at both the edges. So it is observed that there is higher dissolution of LD slag in sodium silicate solution. So these are the morphological images, which shows that mixes containing both solid and liquid forms of sodium hydroxide exhibited flat surfaces with the presence of pores, and the formation of geolites containing micropores hydration products. And on the other hand, the mix which contains solid sodium silicate, it contains uneven and not so compact calcium silicate hydrate CSH gel, and indicating lesser dissolution of LDS in solid sodium silicate activator based mixes. And it has been observed that the mix 6, which is comprised of liquid sodium silicate activator, displayed a very dense and compact morphology. So these are the thermogravimetric analysis, and which shows that the presence of CSH gel, calcium hydroxide and carbonate through significant mass loss peak around 300 degrees Celsius, 450 degrees Celsius and above 600 degrees Celsius. Now mixes containing solid and liquid sodium silicate, the peaks of mass loss at around 300 degrees Celsius is linked with the dehydration of calcium silicate hydrate. So here is the conclusion, which shows that LD slag-based composites containing liquid form of sodium silicate showed 11.2% higher compressive strength than the control mix. Therefore, liquid activators possesses higher dissolution of slag than solid activators. And then LD slag-based composite mix comprising a liquid form of sodium silicate activator displayed a very dense morphology, and therefore, from the conclusions, we can conclude that liquid activators, particularly sodium silicate solution, found more efficient. So these are the publications for reference, and thank you.
Thank you very much. I think this presentation is ready, keynote presentation is ready. Can we have Dr. Rai? I think your presentation is ready. It is ready, right? Yeah. You have a total of 15 minutes.
Yeah, thank you, Chairman and Co-Chairman, for giving me the opportunity. Of course, like the presentation was missing, and therefore the delay was there. So already LC3 we are aware, and if we are talking about the decarbonizations, I think through decarbonizations, when I was discussing with my colleague, then we were thinking of decarbonization. So we used to write D, and after that a gap was maintained, and after that carbonization was used, carbonization. But now we are doing a lot. I think we should clap for all the cement industries. We are doing a lot of things to become decarbonized, right? And now I'm happy to share that everywhere we are writing decarbonization together. So this is when I was doing the experiment, a lot of research work for the decarbonization. So both these words are now together. So this is the effort of all the cement research and the academia. Thank you very much. And as you can see that the grade-wise PPC ratio through the blended, because today I will be talking more about LC3 and the decarbonization step for blended cement. So through the blended cement, if we really want to have this step of decarbonization, then as per the this GCCA India report, out of the total cement produced in our country, 65% volume share is of PPC, that is a blended cement, fly ash based. 27 is OPC, and the rest is PSC and CC. For further CO2 reduction through this blended product, of course, I think LC3 can prove to be the better solutions. Of course, I will take you to that CO2 emissions, that what are the CO2 emissions from the blended product, whether it is of PPC, OPC, PSC, and CC. So this is LC3. We will be talking more about LC3, in which right now, if we are talking about decarbonization, of course, we have to go ahead. Through LC3, if we want to become decarbonized, then we can replace at the right moment and very fast 40% CO2 reduction. That is complete replacing your OPC, which is the volume share is 27%. So LC3 can be best solutions for that. This is the graph, and also that 8% of the total CO2 emitted globally, that is 1.5 billion tons of CO2 annually we are releasing through the cement manufacturing. And there can be the reduction of 40% if we are replacing LC3 with OPC, completely substitution. This is the by yarn tissue, the cement manufacture, these emissions from the CO2 emissions from cement sector. So you can see that if we are comparing from 1962 to 2023, CO2 emissions from cement industry in India has increased from 4.94 million tons to 177 million ton in 2023. India is the second largest CO2 generator that is across the globe. Looking the product-wise CO2 emissions from cement product, the majority comes from the clinker percentage used in the blended product. So why it is coming from clinker? Because everyone is knowing that producing 1 ton of clinker, almost 930 kg of CO2 is being released in the atmosphere. Running into this valid technical reason, I would say that in OPC 90% of clinker is used, and therefore the CO2 emission here will be 0.84 tons per ton of cement, followed by your PPC, where 65% of clinker is being used. So with that, we are releasing around 0.582 ton of CO2 per ton of cement. For PSC and CC product mix, the clinker factor is lower than PPC, but due to unavailability of good quality of slag, where amorphous content is required as per the strength parameter is concerned. Therefore, there are some challenges to meet this CO2 emission to the lower level by these products like PSC and CC. In this scenario, now we are left with only one option, that is LC3 productions, where we can use this calcined clay and directly replace your 27% of OPC, what I shared you in my earlier slides. So there will be reduction of, if I am talking about OPC, from OPC if we are completely substituting, then 0.842 ton of cement per ton of cement CO2 emission, that will be reduced through the LC3 production to 0.43 ton per ton of cement. This is looking into the cement expansion projects. So right now we have the installed capacity of 600 million tons, right? And as per the volume share is concerned, 227 CO2 is emitted by PPC, which occupies 65%. Through OPC it is 136, from PSC it is 16, and similarly from CC it is 3. So if we are completely substituting your OPC with LC3, then by 2030 there will be reduction from total cement production volume share, that is from 382 to 316. Similarly from PPC also, if we completely substitute, because we cannot completely substitute PPC, only for those regions we can substitute where fly ash is a challenge, good quality of fly ash is a challenge. So there, if we are completely replacing PPC out of the total volume share, then it will be reduced from 227 million ton to your 168. and from completely replacing OPC, we will be from 136 to 70. This is India is a developing nation, and of course we have to be in the list of developed, so lot of infrastructure activity has to be continued, and therefore the cement volume is expected to grow by 6 to 8% every year, and also looking into that lot of projects and the volume expansion. So if we are, right now we are in the consumption of 391 million ton of cement production, and our installed capacity is 600 million ton, and we are expecting that the cement consumption in fiscal year 27 is going to be 450. And this is the second slide you can see, second one, there's a region-wise installed capacity. For north, it is 22% of the total cement manufacturing capacity. In south, it is 33%, followed by east 19%, west 13%, and central 13%. So we have a good options for producing LC3 in south, where our capacity is more, followed by north, which is 22%. This is, of course, LC3 can prove to be a very benefiting step, and also a decarbonization step for other talks, that is limestone reserves. Because when you will be replacing the clinker, because where your limestone is being consumed, high-grade limestone is being consumed, then by producing LC3, whatever the clinker you are consuming for making the cement, as per the volume is concerned, as per the cement consumption trade is concerned, the 40% can be replaced by LC3. So as you know that 1.6 ton of limestone is required for producing 1 ton of your clinker. Similarly, with LC3, looking into the volume expansion, you can you can increase the deposit, that is limestone reserves. This is the estimated growth limestone requirement by the cement industry, looking the installed capacity and the further growth plans. Because in the morning you might have heard from one of our eminent leader, that he told that we are expecting around 900 million ton production capacity. So of course the limestone can become a constraint. Looking into the limestone constraint, I think we are left with only 27 years. So if we really want to store our reserves for to increase the life of the cement industry, then we have to take this step now, that we have to go with blended cement like LC3. This is the total proved reserve of limestone deposit as of 2010. This is this IABM report, and you can see that 14,926 million tons was the proved reserves. Of course, we have many reserves, huge quantity, but these are the proved reserves. The total cement production in 2015, it was 366 million tons, which grew to 395 million tons. Estimated cement production by 2025, it is 550 million tons. So looking at the rate of 550 million ton, our limestone deposit is only for the next 27 years. So therefore, we have to completely replace OPC, and I request everybody to educate the people. Even the government body is also included in that no, OPC should be completely replaced with the blended cement like LC3, where the huge opportunity is there. And I think in my next, previous presentation, that was of previous session, already LC3 was discussed. As per the performance is concerned, it is better than OPC. So we should push LC3 in a more go way. So increase if we are completely replacing OPC through this LC3, our limestone reserves will grow by 11%. Now we are talking about this clay, because for producing the LC3 cement, clay is very important, and of course the important thing is kaolin, because kaolin is something which is being calcined, and it is converted into metakaolin. And you know that when cement is being reacted, your calcium silicate hydrate gel is formed. But since your kaolin contains maximum percentage of alumina, so that the reactivity is better, and it is being proven also by a lot of studies on LC3, that your cash is formed, that is calcium aluminate silicate hydrate gel, which is more reactive than the calcium silicate hydrate. So this is the availability of the calcined clay, where lot of options are there, where we can convert OPC into this LC3. Maximum is Gujarat 48%, followed by Kerala 23%. So of course South, I told you, maximum installed capacity is also there for the cement production. So there we can go with LC3. I will not go into the details. This is the production and composition of LC3. You know that chemistry, how it is working, and in the brief I told you that the CSS gel, which is very important to give the strength, here it is converted into CAS, which is calcium aluminosilicate hydrate gel. So this is kaolin, which is converted into metakaolin at the temperature of 800 degrees Celsius. So it can save your fuel as well, if we are talking about the thermal consumptions. This is the science behind LC3 reactions, and as I think everybody is aware, lot of lectures and lot of presentations already have given to you. If you might be aware of all this reaction mechanism now. So I will not go into the details, but as you talking about the microstructure, reduced porosity will be there, particle packing will be good, right, and increase CS gel, and also calcium aluminum hydrate gel will be better here. Of course, some recommendations and way forward is there to further encourage to put LC3 into the better picture, and as I told you, to convert OPC totally into LC3. That is, we have to control the OPC production in the country, right? Many people are asking for OPC, so we have to discourage them. We have to educate them that now OPC is not better than your LC3 cement. If we are talking about the strength, if we are talking about the durability, whatever the studies is being carried about from the researchers, you have to bring them, you have to educate them. Just like PPC, once upon a time it was a challenge, right? So I am very thankful to BIS also, who has released the IS code of LC3. And so low carbon cement in the government tenders also we have to push. I think BIS is doing a good job in that. So in the government tender also LC3 is being pushed to be used. Of course, I will request, because being from the cement manufacturing fraternity, if we really want to have a better cost edge, which is also one of the important parameters. So I think LC3 should be included in a special category like low carbon cement, and also with differential official incentives and subsidies. Also, of course, in some regions like North, there is a scarcity of good quality of fly ash because of the lack of power plant, so we are facing problem in PPC as well to increase that blended cement share of PPC because of getting good quality. So I will request BIS to have some revisit to the specifications needed in that, and really, of course, from 65% also for PPC also we can push it better. Of course, now I will request my team member Akhileshwar Upadhyay from the R&D, who has done some experimental work on LC3, to give you the overview and make you confident that why LC3 is important to use it based on the technical aspect. Thank you very much.
Thank you, Dr. V. Thank you very much. I think we'll go to the next.
No, I will continue. I will take few minutes to complete the experimental work on LC3. Thank you, sir, for your valuable insight and talk about the significance of LC3. Good evening to all. I go straight away on the experimental work, what we have carried out. These are the contents. We all know LC3 is limestone calcined clay cement. It is one of the blended cement. It provides further scope of substitution, energy intensive component of cement, that is clinker. We all know we have carried out experiment with clay available nearby of our plant. Test results was encouraging, which has been displayed in forthcoming slides. Nowadays, we all know that power generation based on fossil fuel is getting switched over to the renewable energy, which may cause the scarcity of the fly ash. Also, slag is not available in North and South India, where it may be the prominent option. This is the Indian standard requirement to produce LC3. It has been compared with PPC. The major thing is that the clinker would be in the range of 50 to 80%. If we use OPC 43 grade cement to produce LC3, then it would be in the range of 55 to 85%. Limestone would be in the range of 5 to 20%. Calcined clay would be in the range of 10 to 35%. Blend would be minimum 400 meter square per kg. Loss on ignition would be maximum 10%. And strength is similar to the OPC 43 grade cement. I think some technical glitch had there. Okay. So we have prepared the LC3 and PPC in our laboratory ball mill and evaluate the performance of both cement. This is the chemical analysis of raw material. We have same clinker and gypsum has been used to prepare LC3 and PPC. We have carried out XRD analysis of raw clay sample and found it suitable. Major mineral phases is keonite, muscovite, calcite. After calcination at 800 degrees Celsius, more than 80% content gets converted into the amorphous content. This majority of amorphous content is nothing but metakaolin. However, in fly ash, the amorphous content is in the range of 45 to 50%. So this is the significant difference. We have also carried out thermogravimetric analysis to derive the water of crystallization. Keonite content has been calculated by the loss on ignition between the 300 to 750 degrees Celsius. The content of the LC3 was 15% limestone, 30% calcined clay, 50% clinker, and remaining was gypsum. We have separately ground the calcined clay and mixed with grounded clinker, limestone, and gypsum. Similarly, PPC has been prepared by mixing of fly ash with grounded clinker and gypsum. The lime reactivity of calcined clay was more than 8 MPa. This is the physical test results of both cement. You can see here that the water demand has substantially increased in LC3. Setting time got reduced compared to the PPC, but the early edge strength development is very comparatively high. At 3 days, it is approximately high by 5 MPa, and at 7 days, it is approximately by 2 MPa. At 28 days, strength is approximately same. So we all know the loss on ignition in LC3 is due to the limestone content used. Conversion factor is just double. We have carried out the workability test and compared with PPC. Out of this test, it has been arrived that admixture content is approximately increased by 40% to retain the same workability. You can see from this graph that setting time got reduced by almost 60 to 70 minutes. This is maybe due to the high blend. So the region of high early strength development has been predicted maybe on account of high fineness cast gel formation, reaction of calcium aluminate and calcium carbonate, which reduces the chances of conversion of trisulfate to monosulfate phases, but 28 days strength is approximately same, maybe due to the lower clinker factor. So we can say that LC3 is the potential alternative of the other blended cement. It is a low heat cement. Out of this study, this study revealed that the other blended cement has the key downside that it has lower early strength development, but in the LC3, this has been overcome. So only limitation is that this is higher admixture demand. Thank you.
Thank you very much. So both of you together have shed a lot of light on LC3, but the fact remains, earlier maybe you used to say BIS has not come out with a code. Now the answer is ready. BIS has come up with a code. Now the next question is why still LC3 is not available in the market? That question remains, but however, you have given a lot of inputs on LC3 and its these. Thank you very much.
Thank you.
We'll go to the next paper. This is by Sunil, Sachin, Mr. Chaudhary and Bansal, who would present this paper, Innovative Utilization of Industrial Byproducts. This team is from Mangalam Cements. Anybody is present, will present this paper? No? Okay. Then the next paper, Selective Concrete Recycling. Yes, Crete. Yeah. Mr. Reformat? Yeah. Welcome to you, and please start the presentation. You have 8 minutes time.
Thank you very much, Mr. Chairman. Thank you, dear audience, for being here in this late evening hours. I want to speed up my short talk about selective concrete recycling. My name is Martin Reformat from the LOESCHE company. I think I don't have to introduce the LOESCHE company. We are a very traditional, family-owned German company that has the core equipment of vertical roller mills. I think you know them from the raw milling, from the fine milling in the cement or slag sector. But today I want to take you on a journey of concrete recycling. As you know, your Prime Minister had a very great speech at the COP26. I think it was last year. So it was a very strong statement for decarbonizing the Indian cement sector or the Indian country as a whole. So you are facing, or we are all facing, a growing population, especially in India, and along with that we have a strong need for environmental protection because every citizen needs infrastructures. They need hospitals, they need housing, and all this comes along with a huge amount of cement, and the cement is only the glue for the concrete. So we have to talk about concrete when these buildings comes to a life end. So, so my statement to that is the time to act is right now. So we are, and you are not too late. We as LOESCHE, we have always been green. Not only our slogan or our brand was green, but our mindset also. Our owner, Dr. LOESCHE, is very, let's say, addicted to get more efficient grinding devices or to go into new fields of grinding and beyond that. My colleague Andre Trumer told you in the last session about C-clay, our green key solution for clay calcination. I want to widen your sight into the so-called green key solutions. This is our brand for products from LOESCHE to save CO2 on the one hand, but also, and this is I think very important for you as well, to save the resources, natural resources like gravel and sand. This is actually Crete I want to talk about. We also can talk about at our booth or our conference room, meeting room about alternative fuels, about slag enhancement. This is a great topic to utilize slag for cementitious tasks. We are developing H2 burners, hydrogen burners, and also ultra-fine materials. But let's come to the initial situation. Worldwide, there are a huge amount of CDW, construction and demolition waste, and half of that is around concrete, old crushed concrete or demolition concrete. In India, it's around 150 million tons every year. So what is done right now is it's just dumped, or in the best case, it's used as a filling material for road construction or earthworks. But this is without CO2 effect. What we do at LOESCHE, and I will show you the detail in the next slide, we can process this material, can get the sand out of it, can get the gravel out of it, and can also get the so-called cement stone out of it to get an SCM. So with that, we can close material cycles. So the principal process of that is, I think you know the vertical roller mill. We feed our vertical roller mill with so-called crushed concrete. It goes on our table, goes under the rollers. It's comminuted, but only by gentle grinding, not grinding to a certain extent, but gentle grinding. And with that, we can, let's say, desagglomerate our crushed concrete into cement stone, sand, and gravel by the share of around 15% cement stone and the rest 50% sand and 35% of gravel. This is working because we have a grinding bed comminution, not a particle comminution, and we have the gas flow from bottom to top. We have a classifier inside our vertical roller mill, and we can dry in one process. This is a nice, let's say, a nice initial situation for our concrete recycling. And this process, by the way, was patented 10 years ago. This is the picture of our products. You see the feed material on the left side, the gravel, the sand, and the cement stone. By the way, the cement stone has a fineness of around 4,000 to 5,000 plane, so exactly in this range of cement. What to do with the products, you may ask? We can use these products in various ways. On the one hand, of course, sand and gravel will go into fresh concrete via ready-mix stations. This is quite normal and is applied right now. What we also can do with our cement stone, we can use it on the one hand as a clinker raw meal, so we can exchange limestone with this material. And by the way, this is CO2-free material because it was burned at some time. We can use it directly as a filler. That means we can replace Portland cement out of our, or clinker out of our cement composition. And we can also use it as a CO2 acceptor for CCUS, for carbon capture and utilization in this case. So we have plenty of possibilities to use that products. Your material, you may ask what to do with that. What we can do is we can receive your material in Germany in our technical center. We have 4 fully automated grinding devices over there with a very small table diameter of 36 centimeters. These, let's say our babies, our mill babies, we use since decades for the layout of the big mills, and it works perfectly. We can have a look at all test parameters you can imagine, like throughput, energy consumption, the wear. Wear is a very big topic with these abrasive materials. So we can check your material and tell you how to process that. And another topic, but unfortunately I only have 8 minutes, is a mobile plant. So we can put our machine into overseas containers, let's say 2 or 3 maybe, and with that you have a whole plant to process your CDW or your concrete your crushed concrete to get exactly gravel, sand, and cement stone. You grind and dry at one stage. The capacity is up to 4 or let's say 5 tons per hour. So perfect for demolition tasks. You put it on a demolition site, you process your material, and after you finished, you can go one demolition site further. We can pack and unpack it into a few days. Yeah, a short summary, and this is my end, not my end, but the end of the presentation. With Crete, our grinding, concrete grinding and selective grinding product, you can do real urban mining. Urban mining is, let's say, the topic for the next decades. You can use local products, local waste to generate new products out of it. You can save, therefore, natural aggregates and virgin materials. This is, by the way, very beneficial for limestone-poor regions to, let's say, extend the lifetime of your limestone mines. And so on, we can have CO2 reduced raw material, and we can protect landfill area. So thank you very much for your time. You can visit me, you can visit our colleagues from LOESCHE at stall 7 to 9 at the exhibition hall. Thank you very much.
Thank you very much. We have 2 more papers. We'll quickly complete this. The next is the team from Saudi Arabia. It is about replacing a hazardous radioactive PGNA analyzer. Saudi Arabia and Switzerland. Yeah.
Yes, good evening, everyone. Thank you for still being in attendance. Mr. Chairman, I would like to dive right in. Very short introduction, SpectraFlow Analytics, who we are. We are a management buyout from ABB, so the technology I will be presenting on was developed by ABB in Switzerland, and by today we have more than 80 installations, whereas around about 50% of these are in the cement industry and the other part is in the minerals industry. I don't want to spend too much time on the technology, just the point that there is no radioactive sources for these online analyzers, CBA analyzers, online chemical analyzers, whatever you want to call them in the end. We use radioactive sources. I'm very happy to introduce more on the technology for those who have questions at our stall 93 later on. Not later on, probably tomorrow. Sorry. Good, I will skip to the correct page. Okay, typical installation locations, it's the classic installation location at the stockpile that most of the users have an online analyzer, CBA, installed. There also a radiation-free analyzer can be installed. The second classic one is at the raw mill. We install it behind the raw mill on top of the air slide. I think the more innovative versions come when we look at the fuels. If it's coal, if it's alternative fuels, the technology can measure calorific value, ash, chlorine, moisture, so everything that is relevant in case of coal, of course also sulfur. We can measure the clinker behind the kiln for free lime and clinker composition, clinker minerals, and the same way we can measure the cement in the air slide behind the cement mill for the clinker phases, and I say that very specifically because the technology is sensitive to mineralogy. So we can calibrate and measure mineral phases directly, not just elements or oxide-based. So to the topic of today, Tabuk Cement, located in Saudi Arabia by the Red Sea. First line was taken in operation in '98, 4,300 tons. Second line, 5,000 tons in 2017. Today they operate 3 cement mills with a total of 9,600 ton per day capacity. The local challenges are that they have a very diverse raw material resources, including dolomitic and dolomite material, and the crusher goes with a single feed, so they have to really properly prepare and bring the trucks to the crusher to build their stockpile. The situation was that a radioactive analyzer was installed. The challenges the team faced, the local team faced, was safety concerns, the cost for the sources, but also to fulfill all the regulatory requirements, and the availability of the equipment, which first of all meant can the sources be available right on time when they are needed, but also the service requirements that came up and recalibration requirements. In 2022, new sources were required, and that was basically the time Tabuk looked at alternative online analyzers, cross-belt analyzers, and a SpectraFlow near-infrared analyzer was installed in 2023. And the following goals were achieved. There were no legal requirements anymore. Not for the operation, not for the import. The OPEX was drastically reduced, first of all, due to the completely different price in sources. You just have to replace halogen light bulbs, but also the service and permitting requirements, and they saw a much improved availability of the equipment. The benefits were further a consistent and high quality pile stacking, which they have seen, first of all, by XRF back calculation, which is the common method of evaluating your CBA functionality and quality. And second of all, when you look at the consumption of your additives at the raw mill, what is the stability of the feed that you can take from the pile, and how much do you need to variate with the additive materials. And there the standard deviation over 16 piles for the pile material was 0.86%, and the standard deviation of the schist which they added also was around 0.85%, so very low. A second point I would like to raise nowadays, especially towards the decision makers in the room and the decision makers in the cement industry, is what should be today the main design, the main considerations for selecting an online analyzer. As we hear basically in every presentation, the cement industry is under a kind of magnifying glass. You are tasked to be greener, to be more ecological, to be employee, not employer friendly, but employee friendly, and the branding that you need to put on your labels, on your logo, is really a must. So the question you need to ask yourself is, how will this affect the strategy and the decisions of the board and also of the regulatory body in the future? Will operation permits, if you have to brand as green, as ecological, will permits be given in the future for the use of radioactive sources, of hazardous materials? Discussions I had here during the conference is that a lot of these radioactive and gamma meters, when it comes to levels or level sensors or other equipment, are already being step by step eliminated. So the question is, will you be able, if you invest today, to still use your equipment 5 or 10 years down the road? I'm not saying a change is coming tomorrow. Saudi Arabia, for example, has done that change already and has banned the use of californium sources and other radioactive sources. So the question is, do these questions influence investment decisions for investments which have a 15+ year life cycle? And of course, furthermore, you need to have a technical reassurance. So is it a proven technology and accuracy? What about the OPEX? And overall, does this technology contribute to my CO2 reduction? In a nutshell, basically, the SpectraFlow analyzer, the SpectraFlow technology based on near-infrared analysis, fulfills all of the requirements above. It also fulfills the requirements of like some of the presentations that we have seen. You talk about new types of cement, you talk about recycling raw materials, but in the end you want to know what are you actually putting in your cement, or what are you actually using, what kinds of materials are you blending, what's the calcination percentage, what's the calcination rate of your clay, of your limestone that you are using. So all of these materials, the more variable, the more different materials you put into your cement, the more control you need and the more process control you need. I'm not necessarily talking about control in the laboratory. You need to do your quality control. A process analyzer will never replace a laboratory, but you can reduce the feed to the laboratory and let the lab really focus on their quality analysis and let the process control be done by a process analyzer, which is inline, not at line, and which gives you minute-by-minute instant results. For those of you I managed to put asleep, just summarizing the advantages of the near-infrared technology: no radiation or permits, no limitation on operating lifetime, therefore. The sources enable a low OPEX in terms of cost and service. It's a proven technology. We have enough installations in the market for cement and the minerals industry, and it can be used for fuels and blended cements as well. And with that, I thank you for your attention, and in case there are any questions, we will be there for you tomorrow at stall 93. And this is the group of Tabuk Cement after the completion of the project. Thank you very much.
Thank you, Ms. Petra. That was a good presentation. And now we move on to the last presentation of the day. It is on advancements in shotcrete application technology for the cement industry.
Good evening, ladies and gentlemen, and I too must thank you for your patience at being here still at the final presentation of the day. I applaud your patience, and I will do my very best to make it worth your while. I'm here to talk about shotcrete, and shotcrete is one of a number of different techniques for installing monolithic refractories into cement plant applications. It sits alongside vibrocasting, gunniting, and the use of precast shapes. As an installer and a manufacturer, it would be foolish of me to suggest that any one of these techniques is always exclusively the right option, because there are many different applications, and the different procedures, the different techniques will be the optimum one on different occasions. However, if you're wanting to make a volume, time-sensitive, flexible installation where you're putting material into conditions where it will suffer extreme service environment, then shotcrete most definitely is the technique that you would need to consider. So shotcrete technology was initially developed in the 1980s, 1990s in the United States, and in the late 1990s it managed to make its way across the Atlantic to Europe, which is when I became involved with shotcrete technology. In these early days, all the development work in Europe was associated with the cement industry. So although today shotcrete is used in many industries in considerably different applications, cement was the starting point within the European development of shotcrete technology. And today it's used extensively for making lining repairs to the coolers and the preheater towers of major cement companies around the world. Although shotcrete material technology has progressed quite significantly over the years, unfortunately the application technique has tended to be stubbornly lagging behind. Now, as a team of manufacturers and installers, we decided that we wanted to try to help bring the application technique up to the standard of the materials technology. The simple fact is that you can spend a lot of money developing a very sophisticated material, but if you take your eye off the ball when it comes to the installation, then all your time and effort has been wasted. So essentially we are trying to carry out a catch-up progress. Our focus has been on efficiency, consistency and safety, but we've also tried to introduce a PLC control system that allows us to eliminate the human factor during the installation process and the associated inconsistencies that come with that. We've also tried to adopt a philosophy of plug and play and modularization. And I've picked a few simple examples to try and explain what we're doing, but the most obvious one is discharging material into the mixer. On the top photograph there, you can see that a bulk bag is swung over the top of the mixer. There is an operator stood on a platform, elevated platform, and then the bag is discharged into the mill. Well, there's an element of danger there for the operator, and when that bag is opened, he will disappear in a cloud of dust. So it's not a very pleasant working environment. We look now at the use of completely lidded mixers with interlock safety systems on them, and the use of quick release dust-tight connectors so that we can actually contemplate now delivering the material discharged at ground level through an enclosed distribution system directly into the mixer. And there's also the potential there for using localized dust extraction down at the ground level. The next point to consider is water addition. Water addition is critical in the installation of monolithic refractories because water equates to porosity. The more water you put in the mixing stage, the more porosity you have when the product is in service, and that will impact fairly significantly on the ultimate service performance. So, traditionally, people have used simple things like dump boxes where you literally fill the water up on a bucket system which you tip in, or use of simple mechanical metering devices, which tend to be very unreliable and certainly inaccurate. At the same time, you would have an operator stood on that platform, and invariably he will have a hose pipe with him, and he will be looking into the mixer and saying, yes, I think maybe a little bit more water. Here we're tending to rely very much on what we refer to cynically as the calibrated eyeball of the operator. And we're trying to eliminate that inconsistency from the mixing process. And so we've started to use these contactless water meters. When the bags are swung over, they're all barcoded. The barcode is read before the material is discharged into the mixer. These PLC system then measures the water temperature, the water flow rate, and it all collects this information, sends it to the cloud. All the detail can be viewed remotely, and all the data is stored for traceability at a later stage. So we're certainly looking to try to improve the accuracy of the installation in that respect. When we look at then mixing and we've added the water, how do you know when is the optimum point in which to discharge the mixer? Again, you come back to the operator's calibrated eyeball. He will look in there and say, yes, I think this is okay. Well, we wanted to try and bring something a little bit more scientific to that. So in actual fact, what we do is we measure the power demand required by the mixing unit. When you put a dry powder product into the mixer, it pulls very little current, it moves quite easily. As you add the water, the material begins to gel, it becomes a little bit more plastic, and that power demand increases. And you can plot a graph of the power demand. It rises to a peak, it then drops slightly and begins to plateau. And it's the point on the plateau which is where you know that the material is completely mixed. So each product will have its own characteristic graph. Different products may be slightly different shape, but you should have a complete degree of consistency if you're mixing one product. Again, going back to the PLC system, this is plotting the graph for each bag of material that goes in. All that data is being saved to the cloud, and the mixer will not allow you to discharge the product until it has reached the right mixing point according to the graph. And if we then move on, another simple system that we started to use is the use of polyurethane liners and paddles. Traditionally, you would have hard steel liners and paddles, and we would say that between 300 and 500 tons you would have to replace these. When we started to use the polyurethane, we weren't all that confident about its potential success, but we've had these units, liners in service now for 5 years, and we haven't had to replace them. So they are definite and significant improvement. Finally, the point that I want to talk about is actually taking the operator away from the mixer platform, putting in a booth where he has a control panel in front of him. He's sat at a chair. He has a series of cameras in front of him, one looking at the discharge and material of the bags into the mixer, the discharge from the mixer. He has then cameras at the point of installation, and he can control the mixer and the pump just as a one-man operation. We'll also have a unit up where the installation will be taking place, say in a preheated tower, and the operator who is applying the material at that point also has a button that he can press so that he can stop the mixer if at any point he wants to. He would then automatically backs off to allow release of the pressure so that the nozzles can be disconnected. Finally, we wanted to bring in the philosophy of modularization, where we're looking to that the mixer can be released on 8 bolts and pulled out one way, the pump can be released on 8 bolts and pulled out another way, and even in the PLC and the electronics control system, everything is built up of standard units that can be removed very easily.
Time.
That's it. Thank you.
Good evening, everyone. Just a few words before we close up. We had a good keynote paper from Dr. A.K. Rai from Shri Cement. Just one comment. BIS is the national standards body, but we are not the regulators. So it's you give us the subject, we will be making the standard, but regulation, it's beyond our scope and ambit of BIS. Thank you. Then we had a good presentation by Sahana CM from IISc Bangalore regarding development of activated biochar and its application in concrete. Only one thing, ma'am, was fine. I think you should have given some comments on the durability issue also of the concrete, because you had more presented on the strength factor. Third presentation was the influence of solid and liquid activators on the performance of LD slag-based composite binder. It was a good paper. let's see in future what research we get from it, and then we can think about development. There was no speaker from Mangalam Cement. We had a presentation for selective concrete recycling from Mr. M. Reformat from LOESCHE, Germany. We had given that how to go about this aspect in the European context. Then finally coming to the replacement of the prompt gamma neutral activation analysis by the near infrared analysis from Madam Petra Mullen from Saudi Arabia. From Switzerland, Spectra Flow Analytics, Switzerland. Ma'am, only thing is that you have not given the cost, that financial aspect of both the things. Okay, thank you. And finally, we had seen the advancement in shotcrete technology in the cement industry from Trevor Staten. We are shortage of time, so we'll just take the questions during the dinner, and there we can thrash out your questions. Thank you, everyone. So over to Chairman, sir.
Thank you very much, sir. You have summarized the whole thing. Thank you all the presenters who have done an excellent job. And again, the other sessions are also over now. Therefore, we are deferring this question. Any questions? Anyway, those who ask question and those who are expected to answer, both of us would be at the dining table. Therefore, we can make use of that. With this, I thank NCB for giving us the opportunity, and I thank Mr. Jaipayan Bhadra from BIS for effectively running this program, and thank you also. Thank you.
Thank you, sir. Now I request our chairman and co-chairman to present the memento to our keynote speaker, Dr. Abhishek Kumar Rai. I would also request to all the presenters to please come on the stage. Ms. Jyoti, Ms. Sahana, Dr. Martin, Ms. Petra, Mr. Trevor. Please come on the stage. Now I would request Dr. Sanjay Mandra to please present the memento to our chairman and co-chairman as a token of respect. We would again like to thank our chairman and co-chairman for their esteemed presence. Thank you, sir. As we conclude this enriching session, we invite you all to join us for a delightful dinner, where you can further network and discuss today's insight. The dinner is at Exhibition Hall 1C. Tomorrow's technical session will start at sharp 9 p.m. So all the presenters are requested to please be present at time. Thank you all.